All right, in this video, I'm going to be going through the AMC 12A from 2019. And I haven't seen these problems before, and I'm going to be trying to do this in real time with no edits and 75 minutes, just like the usual test, and no calculators. And my goal is, well, partly to see how well I do, but also to show some techniques for solving these problems and just general test-taking techniques. So I'm going to try to go through them in order, but I will probably end up skipping around with the later problems because that there are some subject areas that I'm weaker in, so I'll probably gravitate toward the problems that I know how to do. Okay, so let's start. Okay, so I'll be posting I'll have the problems on the side of the video so that you can see them as I work on them. Okay, so problem 1 says the area of a pizza with radius 4 inches is n% larger than the area of a pizza with radius 3 inches. What is the integer closest to n? Well, okay. So the ratio of the areas is the square of the ratio of the radii. So it's just going to be 4/3 squared. That's the ratio, which is 16/9, which is 1 point, well, it's 1 plus 7/9, and 1/9 is 0.1 repeating. So it's 1.777 and so on. So it should be about 78% larger, and that is E. Okay. Problem 2. A is 150% of B. What percent of A is 3B? Okay, so A is 1.5B, and what percent of A is 3B? So B is 2/3 of A, so 3B is twice A. So 3B is 2A, so that's 200% of A, so that's D. Okay. Number 3. Okay, now I'm gonna actually have to do some work here. Okay, so a box contains 28 red balls, 20 green balls, 19 yellow, 13 blue, 11 white, and 9 black. What is the minimum number of balls that have to be drawn without replacement to guarantee that at least 15 balls of a single color will be drawn? Okay, so I think this is basically something like the pigeonhole principle. So I'm going to try drawing, I'm going to see what happens in the worst case scenario. Okay, so I can draw 9 blacks with 11 whites and 13 blues without doing anything. Okay, so 9 white plus 11 black plus 13 blue. And I can do all that and I'll never get 15 balls of a single color. And I can take 14 yellows, 14 greens, and 14 reds. 14 yellow plus 14 green plus 14 red. Okay, what is that? 20, 33, 47, 61, 75. So I think if I take 76 balls, I'll have to get 15 of a single color. So that is B. Okay, let me just double check my arithmetic here. Yeah, okay. 4. What is the greatest number of consecutive integers whose sum is 45? Okay. Oh, I think I know. Okay, so what I can do is I can take, if I take an interval that's symmetric around the origin, so like negative 10 to 10, and add all those up, I'll get 0. So if I do that trick here, if I sum minus 44 to 44, I'll get 0. And then I have a 45 at the end. So minus 44 to 45 is, that should be 90 numbers. So 90 numbers. And that's the most cancellation I can get. So that should be the maximum number. So that's D. Okay. Okay, number 5. Two lines with slope 1/2 and 2 intersect at 2, 2. What's the area of the triangle enclosed by the two lines in line x plus y equals 10? Okay, I'm definitely going to have to draw a picture here. Okay, it's not going to be a very good one, but just a rough sketch. Okay, so here is 2, 2. One of them has slope 2. So that's the line y equals, oh wait, sorry, new picture. Okay, so it's line y equals 2x. Here. Okay. So this is y equals 2x, and then I have y equals x over 2, or sorry, no, it's not y equals 2x, it's y equals 2x minus 2. Then I have y equals 1/2 x plus 1. Okay, and then I'm going to have some triangle out here made by x plus y equals 10. Okay, well, okay, these two lines are symmetric around line y equals x because their slopes are reciprocals. So I'm going to get an isosceles triangle, actually. So let me find the intersection points. So one of them is 2, 2. And then y equals 2x minus 2 and x plus y is 10. So that's 3x minus 2 equals 10 when I plug it in. So x is 4 and y is 6. So that's 4, 6. And then this should be 6, 4 if I've done things correctly. If I plug in 6, yeah, I get 3 plus 1, which is 4. Okay. So I've got the midpoint here is 5, 5. Okay, so the height is this distance here, which is 3 root 2, because it's at a 45-degree angle. And then the base here is, I go over 2 and down 2, so that's 2 root 2. So the area is 1/2 times base times height. Okay, so that's 6 times 2 over 2, so that's 6. Okay, and that's C. All right. Okay, problem 6. Okay, so okay, this is a weird one. Okay, so I have this diagram that looks something like, so I've got a square, square here, square here. So they're evenly spaced and alternating. And they've got these weird line segments coming out. Okay, and it goes off infinitely in both directions. And we want to know which transformations other than the identity will map the figure to itself. Okay, so and this is the line L. Okay, some rotation around a point of line L. Well, yes, that should work, because if I pick, say, the midpoint right between these two and do a 180-degree rotation, that should take it to itself. So rotation by 180, so that should work. Some translation in the direction parallel to line L. Well, yes, if I translate it over this distance so that the squares line up again, that'll work. So translation works. Okay. The reflection across line L. Well, no, that won't. work because then the lines will be going in the wrong direction. So that won't work. Some reflection across a line perpendicular to line L. Okay, so that'll be something like this. I don't think that'll work either because again, these little lines coming out will be going in the wrong direction. So I think it's just two of those options. So that's C. Okay, problem 7. Okay, Melanie has the 365 numbers that are the dates in the months of 2019, and she computes the median, mean, and modes. Let D be the median of the modes. Okay, which of the following statements is true? Okay, so the modes, when it tells us how many of each number there are. So there are 12 ones, twos, threes, and so on up to 28s. So those are the modes. So D is the median of the modes, well, the median of a bunch of the median of a bunch of ones, twos, up to 28s is the number right in the middle, which is 14.5. The mean, what will the mean be? Well, the mean will definitely be bigger than 14.5 because that would be the mean of a bunch of ones, twos, and 28s, but they're also bigger numbers. So the mean will be something like, well, almost all of the months have either 30 or 31 days. So the mean will be at least, sorry, the mean is mu, is at least the mean of 1, 2, 3, up to 30, which is 15.5. Okay, so mu is bigger than 15.5. It'll be strictly bigger because of the 31s. And the median, let me think about that. So we have to go through half of 365 in, so we're looking for the 183rd value. Okay, so I go 183 divided by 12 is about, so it's about 15 times 12. Okay, so I'm looking at the 16th number. So M should be 16. And the mean will be, the mean can't be 16 because that would be the mean if all of the months had 31 days, because 16 will be right in the middle. So yeah. Let me just think about this for a second, just to be sure. So D is definitely the smallest. Then, so that already narrows things down a bit. And then the median should be the largest. So I think it's D is less than U, which is less than M. Okay, I'm gonna go with that one. I'm not totally confident, but I'm gonna go with that. One sec, I need to think about this a little more. Maybe mu is bigger because if I have data that's skewed, the mean is moved by that more than the median generally. So if I had all 1s through 31s, that would have a higher mean than this data set, and that would have a mean of 16. Yeah, I guess this is right. I guess it is E. Okay. I'm not too confident on that one, but I'm bound to make mistakes. Okay, number 8. For a set of 4 distinct lines in a plane, there are exactly n distinct points that lie on 2 or more of the lines. What is the sum of all possible values of n? So I have 4 distinct lines in a plane. I'm just going to draw 4 random lines first. Okay, there's an intersection there. So any 2 of these should intersect somewhere. So there should be 6 intersection points for each of the 6 pairs of lines. Okay, for a set of 4 distinct lines in a plane, there are exactly n distinct points lying to or more of the lines. Okay, so basically it's just asking for the number of possible numbers of intersections. So 6 is definitely a possibility. Can I get 5? Well, yeah, because if I, well, I'm not sure I can actually get 5. Well, if I start with 3 lines, then if none of them are parallel, then they're going to intersect in 3 points. So I could get 4 intersection points if I take a line through that. Well, no, that would be 3. Sorry, let me do that again. Okay, so if I take a line here, that'll be 2 intersection points added on with the initial 3. So 5 is possible. Can I get 4? Let's see. I think so, because I can have, yeah, I could have 2 parallel lines, 2 sets of 2 parallel lines. It'll give me 4. Okay, can I get 3? Yeah, because I can do this and then make one line parallel to another. So I can have this. So 3 is possible. Okay, can I do 2 intersections? I think so. Okay, well, I can definitely do 1 intersection point. That's easy. Okay, so I just need to know if I could do 2 intersections. I'm not sure that I can. I mean, okay, some of the lines are going to have to be parallel. Okay, but if I have 2 parallel lines and I have to add in 2 more, the next one is either going to intersect in 2 points or no points. If I have 2 points, then I'm in trouble because I can't add a 4th line and add no intersections. So I'd have to have 3 lines, and then the next one is going to have either 0 intersections or 3. So I don't think 2 is possible. Okay, so 6 plus 5 plus 4 plus 3 plus 1 is 15 plus, that's 19. Okay, so that's D. Okay. Now for problem 9. Let's see, I'm about 20 minutes in, so that's not too bad. Problem 9, I've got A1 equals 1, A2 equals 3/7, and then I've got this wacky recursion. So AN is an minus 2, an minus 1 over 2 an minus 2 minus an minus 1. Okay, and I want to find a 2019. Okay, well, I think I know the trick. This kind of looks like if I had the reciprocal here, then it would be easier to work with because then I'd have a product in the denominator. So let me take the reciprocal. So I get 2an minus 2 minus an minus 1 over an minus 2, an minus 1. Okay, so 1 over an equals, so I have 2 over an minus 1 minus 1 over an minus 2. Okay, so the reciprocal is a second order recursion. Okay, so let's say bn is 1 over an. So b1 is 1, b2 is 7/3, and then bn is 2bn minus 1 minus bn minus 2. Okay, now this I think should be satisfied by any linear function. So because the characteristic equation is t squared equals 2t minus 1, which is t minus 1 squared equals 0. So that would be something times 1 to the n, which is a constant, plus something times n times 1 to the n. So in general, if I have a double root here, so if I have a double root r, then the sequence will be given by, sorry, bn is something times r to the n plus something else times n r to the n. Okay, that's just a general fact about linear recurrences. If the roots are distinct, then it's simpler than it is just a sum of two exponentials. But if there's a double root, then I have this n here. Okay, so when r is 1, I just get a linear thing. So bn should be something like cn plus d, for some c and d. So c plus d, when I plug in n, I get 1, and 2c plus d is 7/3. Okay, so c, to get c, I subtract those. C is 4/3, and d is minus 1/3. So I should get bn equals 4n minus 1 over 3. So when n is 1, it works. When n is 2, it works. Okay, so then an should be the reciprocal, 3 over 4n minus 1. I guess just to be sure, I'll compute the third term. So I get 1 times 3/7 over 2 minus 3/7. So I multiply both sides, or the top and bottom, by 7. And I end up with 3 over 2 times 7 minus 3, which is 10. Wait, 2 times 7 minus 3, that's 11. Okay, and that does work when I plug it in here. Okay, so A 2019 equals 3 over 4 times 2019 is 8,076, so it's 3 over 8,075. And that's not a multiple of 3. So, and I want to know the sum of the numerator and denominator. So that's 8,078, which is choice E. Okay. Oh, and if you don't know that trick, you can always just try a few small values and see if you find any patterns. Okay. Next up, we have a geometry problem. So I have 13 circles of radius 1 in a larger circle. All the intersections occur at points of tangency. What is the area of the region inside the larger circle? What okay, this is going to be a hard one to recreate. Okay, so I've got a little circle here. That's a good start. And then I've got 6 around it. Oops, those are supposed to be tangent, but you get the idea. Okay, so I've got those 6, and then I have 6 more. 1 here, 1 here, 1 here, 1 here, and 1 here. And then around that, I have the big circle. Okay, so it looks something like this. Okay, so, and all these mini circles have radius 1. Okay. I'm definitely going to use some equilateral triangles here. Oh, I think I know. Okay, so this, if I connect these 3 centers, I get an equilateral triangle. And then this length has radius 1. And then if I take the height of that equilateral triangle, I get the rest of the big radius. Okay, so this has this has side length 1 plus 2 plus 1, which is 4. So then the height, so that's the center, which I'm going to call O. That has radius, or sorry, length 2 root 3, I think. Okay, yeah. Okay, so now it's the radius is 1 plus 2 root 3. Okay, so now I need to know the area of inside the large circle, but outside all the smaller circles. Okay, so the area of the large circle is pi times 1 plus 2 root 3 squared, and then the smaller circles, those each have area pi, so I subtract 13 pi. So pi times 1 plus 2 root 3 squared minus 13 pi. Okay, so I end up with, oh, that's interesting. I get 1 plus 12 here. So that's 13 plus 4 root 3 minus 13. So it's 4 root 3 pi. And that is a, okay. So interestingly, the 13s cancel out, which is strange. But I suppose it's just a coincidence. Oh, this was problem 10. Okay, problem 11. For some positive integer k, the base k representation of 7 over 51 is 0.232323, and so on. Base k. And we want to know what k is. Okay, so well, I have 7 over 51. And on the right side, I have 2 over k plus 3 over k squared plus 2 over k cubed plus 3 over k to the 4th, and so on. Okay, so the 2's, every other term forms a geometric sequence. So 2 over k plus 2 over k cubed, and so on. That's a geometric series with first term 2 over k and then common ratio 1 over k squared. So we get 2k over 1 minus 1 over k squared, and then plus 3 over k, or sorry, yeah, that's right. 3 over k squared over 1 minus 1 over k squared. Okay, so it's a bit of a mess. So I can combine the numerators. 2 over k plus 3 over k squared over 1 minus 1 over k squared. Okay, and then I can multiply the top and bottom by k squared. So I get 2k plus 3 over k squared minus 1, and that should be 7 over 51. Okay. Okay, well, if I want to be a little tricky, k squared minus 1 has to be a multiple of 51. So 17 is a factor of k squared minus 1. So k is plus or minus 1 mod 17. So it's either going to be 15 or 18, or sorry, 16 or 18. Well, and only 16 works, but among all the answer choices, but let me just try it anyway. So 2 times 16 plus 3 over 16 squared minus 1. So the numerator is 35, and then I have a difference of squares here. So that's 15 times 17, and then the 5's cancel, and I end up with 7 over 3 times 17, which is 7 over 51. Okay, so K is 16, which is D. Okie doke. Okay, I'm about half an hour in, so I'd like to get up to 20 problems, but we'll see how that works out. Okay, problem 12. So I have log base 2 of x equals log base y of 16, and xy is 64, and I want to know what log base 2 of x over y all squared is. Okay. Well, I guess I have no choice but to plug in y equals 64 over x and see what I get. So log base 2 of x equals log base, okay, this is going to get messy, 64 over x of 16. Okay, so log base 2 of x is, I'm going to use the change of base formula, so it's log base 2 of 16 over log base 2 of 64 over x. Okay, and this numerator is 4, and then I have log base 2 of 64 minus log base 2 of x, so that's 6 minus log base 2 of x. Okay, so 6 log base 2 of x minus log base 2 of x squared equals 4. Okay, that's a quadratic. I'm not sure it has any nice roots, unfortunately. Well, okay, log base 2 of x over y is log base 2 of x minus log base 2 of y. So I just need to find this quantity. So as long as I find log base 2 of x and log base 2 of y, I'll be good to go. So let me say log base 2 of x is, I don't know, alpha. Okay, so then 6 alpha minus alpha squared is 4. So alpha squared minus 6 alpha plus 4 is 0. So alpha is 3 plus or minus root 36 minus 16, so that's 20. Or sorry, why did I write 3? Sorry, 6 plus or minus root 20 all over 2, so that's 3 plus or minus root 5 over 2. Wait a second. 6, 4. Something's not quite right. What did I do wrong? Because these two things should multiply to 4, but the 2 got canceled out, so it's 3 plus or minus root 5. Okay. So I don't know which one of those it is, but then remember log base 2 of y is log base 2 of 64 over x. So it's 6 minus log base 2 of x. Okay, so I really need, it's just going to be the other root of the quadratic. So I'm going to get 3 plus root 5 minus 3 minus root 5, and that all squared. And the 3's go away, and I get 2 root 5 squared, so that's 20. Okay, so it's 20. Okay. This one looks interesting, a little scary. Okay, so I need to know the number of ways to paint the integers 2 through 9, red, green, or blue, so that each number has a different color from each of its proper divisors. Oh boy. Okay, so each prime has to be a different color from 1. So let's say that, oh wait, no. 1 isn't on the list. Okay. Okay, I'm usually comfortable with number theory, but this is also a counting question, so that's not my strong suit. Okay, well, the primes can be anything. So 2, 3, 4, 5, 6, 7. Okay. So 2 can be anything. 3 can be anything. 5 can be anything. 7 can be anything. Okay. Now 4 just has to be something other than what 2 is. Uh, 6 has to be something other than 2 and 3. And 8 has to be something other than 2 and 4. Okay. And 9 has to be something other than 3. Okay, so I think we need to do casework on the colors of 2 and 3. Okay, so case 1, let's say 2 and 3 are the same color. Okay, so the number of paintings or colorings, I guess, is, okay, so 2 can be anything, so there are 3 choices. Then I have 1 choice for the color of 3 because it has to be the same as the color of 2. I have 2 choices for the color of 4 to be anything other than what 2 is. Then 5 can be anything, so 3 choices. 6 can be anything other than 2 and 3, but 2 and 3 are the same color. So it's anything other than that 1 color we used, so 2 choices. 7 can be anything. 8 can be anything other than 2 and 4. Those are different colors, so it has to be a different color from the rest, so there's only 1 choice. And 9 can be anything other than what 3 is, so 2 choices. Okay, so that's a lot of 3's and 2's. 6 times 6 times 6, so that's 216. Okay, and then case 2, 2 and 3 are different colors. Okay, so then the number of colorings is, okay, so 2 can be anything. 3 has to be something other than what 2 is, so 2 choices there. 4 can be anything other than 2. 5 can be anything. 6 can be anything other than 2 and 3, but 2 and 3 are different colors, so there's just 1 choice there. 7 can be anything. 8 can be anything other than 2 and 4, but that, again, that's just 1 choice. And 9 can be anything other than 3. Okay, so 3 times 2, that's 6. 6, another 6, so 216 again. And total, I get 432 colorings. Okay. So yeah, that seems reasonable. Okay, 14. Okay, so I have this polynomial p of x, which is this big mess, x squared minus 2x plus 2, x squared minus, not 6, c x plus 4. then x squared minus 4x plus 8. And this has to have exactly 4 distinct roots. Okay, that's asking me for the size of c. So the roots of these two things, this one is, if x squared minus 2x plus 2 is 0, then x squared minus 2x plus 1 is minus 1. X minus 1 squared is minus 1. So x is 1 plus or minus I. And then with this one, it should be 2 plus or minus 2i, I think. Yeah. Okay. Okay, so if there are only 4 distinct roots, I already have 4. So I need 2 of them to put in here again that will multiply to 4. So I think the only options are 2 plus 2i and 1 minus I and 2 minus 2i and 1 plus I, because those are, will that work? Yeah, because this is 2 times 1 plus I, 1 minus I, and that's 4. And similarly, this is 2 times 1 minus I, 1 plus I, which is also 4. Okay, so the roots are 2 plus 2i and 1 minus I, and then c is the negative of the sum. So it's 2 plus 2i plus 1 minus I, which is negative 3 plus I think. So then the size of c is root 10. Okay. And that's e. Okay. Well, let me just double check that. Yeah, I think that's right. Okay. Okay, more crazy logs in this next problem. Okay, root log a plus root log b plus log root a. Okay, this is a weird equation. Log root b equals 100. And all 4 terms on the left are positive integers, and log is the base 10 log. Okay. Okay, so I'm gonna introduce a variable for these 2 things here. Okay, so root log a, let's say root log a is u, or let's say x, and root log b is y. So these are both positive integers. So if I square both sides, I get log a is x squared. So a is 10 to the x squared, and b is 10 to the y squared. Oops. Okay, so now I get x plus y plus log of root a is just, root a is 10 to the x squared over 2. So it's x squared over 2 plus y squared over 2 plus 100. Okay, and now these are all integers. Okay. Okay, so I can multiply. Oh, I think I see what to do. I multiply through by 2. I get x squared plus y squared plus 2x plus 2y equals 102. Or no, not 102. 200. I was getting a bit ahead of myself. Okay, now I can add 2 to both sides and complete the square with both of these. So I get 202. So I want to write 202 as a sum of 2 squares. Let me think about how to do that. So I'm going to take squares close to 202 and subtract them and see if I get another square. So 196 doesn't work. 169 doesn't work. 144, no. 121 and 81. Okay. Okay, so x plus 1 is well, x is 10. y is 8. Yeah, 10 squared plus 8 squared is 164 plus 2 times 10 plus 2 times 8. Okay, 10 and 8. So a is 10 to the 10 squared, which is 10 to the 100th. And b is 10 to the 8 squared, which is 10 to the 64. So when you multiply them, you get 10 to the 164, which is d. Okay. Number 16. Oh no, more counting. I'm just gonna skip that one because counting is not my strong suit. Okay, let's go to 17. So sk is the sum of the kth powers of the roots of this polynomial. So sk is the sum of the roots of x cubed minus 5x squared plus 8x minus 13. And it tells us S0, S1, and S2. And A, B, C are real numbers, so that sk plus 1 equals ask plus bsk minus 1 plus csk minus 2. I want to find a plus b plus c. Okay, well, I already know how to do this because if I take a root r of this thing, I know that r cubed is 5r squared minus 8r plus 13. I'm just rearranging the equation. And then if I multiply through by r to the k minus 2, I'm going to get r to the k plus 1 equals 5r to the k minus 8r to the k minus 2. Sorry, 8r to the k minus 1 plus 13r to the k minus 2. And if I add those, I get sk plus 1 equals 5sk minus 8sk minus 1 plus 13sk minus 2. Okay, so it's really just the coefficients of the original polynomial but negated. So the sum of those things is 5 minus 8 plus 13, which is 10. And that is D. Okay, so that really doesn't require much work at all if you're clever. Okay, now we're getting into the tricky ones. Let me look over these next few. Okay, I don't know about 18. Okay, maybe we can do 19. Okay, so I have a triangle ABC with integer side lengths, and cosine of A is 11 over 16. Cosine B is 7/8, and cosine C is minus 1/4. Okay, and I want to find the possible, the least possible perimeter. So I guess I'm just going to bash this out with law of cosines and see what happens. So cosine A is b squared plus c squared minus a squared over 2bc equals 11/16. C squared plus a squared minus b squared over 2ca is 7/8. And a squared plus b squared minus c squared over 2ab is minus 1/4. Okay, let's see what I can do with this. Well, I can get rid of all the 2's. Okay, well, this tells me that 2BC is a multiple of 16, so BC is divisible by 16. AC is divisible by 4. And AB is even. Okay, that's not super helpful, but 16 divides BC. So I'm going to have quite a few multiples of 4. Or multiples of quite a few factors of 4, I should say. And a squared plus b squared minus c squared is negative. So this is going to be obtuse. What's an obtuse angle at C? Cosine B is pretty close to 1. So that means that the angle at B is pretty small. So B should be small. Because cosine B is large. Okay, so B is small. So I should probably have 16B, or sorry, I should probably have most of the factors of 2 coming from C. So I'm gonna say C is a multiple of 8 maybe. So 8 divides C. I'm just gonna write a question mark there. Okay, so I guess we can just see what happens when I plug in C equals 8. Okay, this is just a lot of guesswork. I could go through the algebra, but I think that's going to be pretty painful. Okay, so C is 8. Okay, what do I get? I get b squared minus a squared plus 64 equals, or sorry, over 16b equals 11 over 16. So b squared minus a squared plus 64 is 11. So b squared minus a squared is minus 53. Oh, that's bad. Because 53 is a prime. Okay. And that's a difference of squares. So C is not 8. Okay, so maybe C is 16 then. Okay, so if C is 16, then b squared minus a squared plus 256 over, oh wait, I made a silly mistake. That should be 11b. Okay. So b squared minus 11b minus a squared is minus 64. Okay, so I guess I'm just gonna try some values. Okay, b is 1. All right, how should I do this? A squared is b squared minus 11b plus 64. I'm just gonna try some values and see if I can get a square out of this. So if b is 1, I get 64 plus 1, 65. I get 54, that doesn't work. B is 2, I get 2 squared minus 11 times 2, so that's minus 18, plus 64 is 46. So that doesn't work. B is 3. I get 9 minus 33, that's 40. B is 4, I hope this works. 16 minus 44 plus 64. Oh, that's 36. Okay. B is 4 and A is 6. Let's try that. 4 squared plus 468 maybe. Oh wait, that's bad because they can't all be even. Because then, yeah, 2, 3, 4 work. Oh, this should be 8 divides BC. Okay, maybe I made a mistake and accidentally stumbled on the right thing. So if I scale this down, I get 2, 3, 4. Maybe that works. 2 squared plus 4 squared is 20. Minus 3 squared is 11. And that's 16. C squared plus A squared is 25. Minus 4, that's 21. And then CA is, oops. Wait, let me write this in the right order. A is 3, B is 2, C is 4. Okay, so 2 squared plus 4 squared minus 3 squared is 11. Okay, that one works. C squared plus A squared minus B squared. That's 25, 21 over 24, which is 7/8. Okay, and then I get 13 minus 16, so that's minus 3 over 6. So that, sorry, minus 3 over 12. Okay, so 2, 3, 4 is my triangle. Okay, that was a lot of work for such a simple triangle. So the perimeter is a 9. Okay. Whew. Okie doke. Let's see, I've got about 15 minutes left. So oh, okay. I actually have seen problem 20 before, but I'll explain how to do it. Okay, so I have 2 real numbers that are chosen by flipping a coin. If it lands heads, then it's flipped again, and I either get 0 or 1, depending on the next flip. Or if the first coin flip is tails, then I choose the number uniformly at random from the interval 0 to 1. So I have 4 cases. I could have okay, I could have okay, oops. Okay, so I'm going to write what happens with x and y, and then the probability that the difference is more than a half. So I could start with heads on the first roll, so, or first flip. Okay, or I could do heads, tails, tails, heads, or tails, tails. Okay, that's kind of a messy chart, but okay, so if I get heads on a coin, then on the second flip, it's 0 or 1, each with probability 1/2. So if they're both heads, then they're each going to be 0 or 1, and the probability that their difference is bigger than a half is the probability that my 2 numbers are different. So I either get 0, 1 or 1, 0 out of 4 possibilities. So that's a probability of 1/2. And I should say each of these situations happens with probability 1/2, or sorry, 1/4, because the coin is fair. Okay, heads and tails, well, so x is going to be either 0 or 1 with probability 1/2, and then y is going to be a random number from 0 to 1. So no matter what x is, there's an interval of length 1/2 where y could be. So that's probability 1/2. This is 1/2 as well by symmetry. And then tails is a bit more complicated. So that's saying that x and y are selected randomly from the interval. So for that, we need some geometric probability. So x and y are between 0 and 1. So the total set of possibilities is the unit square. And then I want to know when the difference between x and y is bigger than a half. So I graph y minus x equals a half, and y minus x equals minus a half. So that'll look something like that, I think. So it intersects the square at the midpoints or the sides. And then the area I want is the area in the two triangles, and that's a quarter of the total area, because you could split it up into 4 squares, and the two triangles together make up 1 square. So the probability here is actually only 1/4. All right, so now we have to add up all these probabilities, but we have to account for the fact that these cases each happen with probability 1/4. So I'm going to get 1/4 times a half plus 1/4 times a half plus 1/4 times a half plus 1/4 times a quarter. Okay, so that's a quarter times, I'm factoring out a quarter, 1/2, 2/2, 3/2, 7/4. So I get 7/16. So it's a bit less than a half. Okay. Now we're really getting into the hard ones. Okay. Well, I'm gonna try to do the rest of the algebra and number theory ones at least. I'm not sure about the others. I guess I've got about 10 minutes to do these, so we'll see what we can do. Okay, so 21, it says that z is 1 plus I over root 2. And I want to know this giant mess here, z to the 1 squared plus z to the 2 squared, all the way up to z to the 12 squared times 1 over z to the 1 squared, all the way up to 1 over z to the 12 squared. Okay, so z is an 8th root of unity. So z to the 8th is 1, because it makes a 45-degree angle with the positive x-axis, and it's on the unit circle. So I really just have to look at these exponents mod 8, and squares mod 8 are particularly nice because, 1 second. And okay, so it's okay. Okay, so we just have to take the exponents mod 8, and odd numbers are always 1 mod 8 when you square them, and even numbers are either 0 or 4, depending on if they're multiple, if they're an odd multiple, or how should I say it? If they're divisible by 4 or not. If n is even, and 1 if n is odd. Okay, so I'm just going to write out the exponents mod 8. So I have z to the 1 plus z to the 2 squared is 4. Z to the 1 again, then z to the 4 squared is z to the 0 mod 8. And now it's going to repeat every 4. So I'm going to get this whole thing times 3. And then I'm going to have the same thing, but with the reciprocal. So 1 over z to the 1 plus 1 over z to the 4th plus 1 over z to the 1 plus 1 over z to the 0 times 3. Okay, so that's my whole thing. So it's 9 times 1 plus 2z plus z to the 4th, 1 plus 2 over z plus 1 over z to the 4th. Okay, now how should I do this without it getting too messy? Oh, z to the 4th is minus 1, because z is primitive 8th root of unity. So z to the 4th is minus 1. Okay, so these terms cancel, these terms cancel. So I get 9 times 2z times 2 over z, and then the z's cancel, and I get 36. Okay, so that is C. Okay, 22 is geometry, and that scares me, so I'm skipping that one. Okay, 23. Oh boy, we have some wacky expressions here. So a diamond B equals a to the log base 7 of B. And a heart B, that's a bad heart, is a to the 1 over log base 7 of B. Okay, and we want to know, oh gosh, okay. A3 is 3 heart 2, and AN is N heart N minus 1 diamond with the previous thing. Okay, so let me just decipher what all this is saying. So maybe what I should do is write everything as 7 to the power of something. So A is 7 to the x, B is 7 to the y, then a diamond B is 7 to the x to the log base 7 of B, which is y, so it's 7 to the xy. There should be a B there. And then a heart B should be 7 to the x to the power of 1 over y, so it's 7 to the x over y. Okay, so when I write everything in terms of powers of 7, I'm either multiplying or dividing the exponents. Okay, so AN is, oh boy, N heart, N minus 1 is 7 to the log base 7 of N. Heart, 7 to the log base 7 of N minus 1. And then diamond, N minus 1. Okay, so that's 7 to the log base 7 of N over log base 7 of N minus 1. Diamond, N minus 1. Okay, so if I let Bn be, oops, sorry, Bn be 7 to the, or no, An equals 7 to the Bn, so Bn is log base 7 of An. Then this is saying that 7 to the Bn equals 7 to the log base 7 of N over log base 7 of N minus 1. And then diamond takes the product, so times Bn minus 1. Okay, so Bn is log, I can just write it without the bases, log n over log n minus 1 times Bn minus 1. Okay, so now I can write out B3. So B3, well, okay, A3 is, how should I do this? Okay, B2, I want B 2019 because it's log base 7 of A 2019, which is exactly what I'm looking for. And that's going to be log 2019 over log 2018 times log 2018 over log 2017, all the way down to log 4 over log 3 B3. Okay, so I get log 2019 over log 3 B3. Okay, and what is B3? It's the log of the starting thing. So 3, how should I write this? So, well, A3 is 7 to the log base 7 of 3 over log base 7 of 2. And then B3 is log of that, so it's log base 3 over, or sorry, log base 7 of 3 over log base 7 of 2. So that's log 3 over log 2. Okay, so altogether, I think B 2019 is just log 2019 over log base 2, or log 2, which is log base 2 of 2019. Okay, and then 2 to the 10th is 1024. So 2 to the 11th is 2048, so that's almost this. So it should be D, which is 11. Okay, hope that's right. Now I think I have time for one more problem. One moment. Yeah, I think I have a few more minutes. Okay, I'm not sure. Okay, one is n squared minus 1 factorial over n factorial to the n, an integer. Hey, let me think about this. Well, for example, if n is a prime, then you're gonna be in trouble because I think, yeah, if n is a prime, then I'm gonna have p to the p factors here. And then here I'm gonna have p to the p minus 1 because the multiples of p are p, 2p up to, well, this is just less than p squared. So they're p minus 1 factors. So maybe as long as n is composite, I'm just gonna guess that. How many integers are there? How many primes are there from 2, 3, 5, 7, 11, 13, 17, 23, 29, 31, 37, 41, 43, 47. Okay, I think that's all of them. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So subtract 14, it's, oh, that's not an option. Do I have to subtract the square of a prime? Oh, I probably have to subtract all prime powers. 4, 8, 16, 32. 27. Squares of 5, 25. Squares of 7 is 49. Okay, so that's 5, 10, 14, 18, 22 numbers. Okay, well, that's something's not right here. So let's just forget about that. And my time is pretty much up. So I'm gonna stop there. I'm not yet sure if I got all these right. I'm going to check that. And then I will post a video. And if enough people are interested in this type of thing, I'll make some more videos just like this with maybe other AMC problems or AMY level problems. I don't know if I'm quite at an Olympiad level, but just some other contests from around that level of AMC to AMY. So I might make some more of these.